Today's topic is superconductivity. Now the question arises, what is superconductivity? The phenomena of losing resistivity when a substance is sufficiently cooled to a very low temperature. Here we have the two figures. For a non-superconducting metals, we see that the resistivity doesn't fall to zero when the temperature is at 0 Kelvin. Whereas for a superconducting materials, the temperature is at Tc point, then the resistivity falls to 0. So this is called a superconducting. Next is Meissner effect. When a material is cooled from normal to superconducting state, then there is a exclusion of magnetic line of force, that is called the Meissner effect. Now in the first figure you see that when the temperature is greater than the critical temperature, it's a normal substance and hence the magnetic lines of force are passing through it, that is magnetic flux is there. But in the second figure, when the temperature is less than critical temperature, then the magnetic line of force excluded from the that conductors, that is it is a superconductor which excludes the line of force. Now here this effect was first observed by the Meissner, and he found that the exclusion of flux lines through the superconductor is called Meissner conditions. According to this effect, the magnetic flux density is 0 inside the superconductor. But according to the relation B is equal to mu naught into H plus M. So if B is 0, it means we have the chi value M upon H, that is negative minus 1. This shows that when a substance becomes a superconductor, it behaves like a diamagnetic. But when we use the Maxwell equations, here del cross E is equal to minus dB upon dt. If we put the B is equal to 0, dB upon dt is equal to the 0, then it means B is equal to constant. So here we see that since E is J is equal to sigma E, when E is 0, then when E is non-zero, then V should not be equal to 0. Here we have the simultaneous conditions. It shows that Maxwell equations as well as the diamagnetic behavior contradict each other, and hence we can say that that these two conditions which contradict each other are these are the characteristics of superconducting materials, that it is diamagnetic as well as it effect of the magnetic field. Now for the superconducting state, the material cannot exist in the presence of the magnetic field of critical value even at absolute zero temperatures. It was found that the minimum magnetic field required to destroy the superconducting property of any temperature is given by the Hc is equal to the H naught into 1 minus T upon Tc the whole square, as shown in the slides. H0 is the critical field and T is the temperature below Tc, and Tc is the transition temperatures, that is the critical temperature. Here in the graph we have shown that the up to below the temperature Tc there is a superconducting state, but above the temperature Tc there is a normal state. And here we have also given the experimental values of 2-3 substances. It was found that there are the type 1 and type 2 superconductors. In the type 1 superconductor there is a sudden loss of magnetizations there, whereas in the type 2 semiconductor there is a gradual loss of the magnetizations. In the type 1 semiconductors it exhibit a Meissner effect, whereas in the second type of conductor it do not exhibit the Meissner effect completely. Here the critical magnetic field is 0.1 Tesla, whereas in the Type 2 superconductor, the critical magnetic field varies approximately up to 30 Tesla. There are the two magnetic field state in the type 2 superconductors. Here is in the type 1 type superconductor, there is no mixed state, whereas in the type 2 semiconductor, you can see in the graph that there are the two states. One is the mixed state, one is the pure superconducting state, and after that there is a normal state. At Hc1 up to Hc1 there is a superconducting state, and Hc1 to Hc2 state there is a mixed state, and after Hc2 there is a normal state as shown in the second graph. These are called type 1 superconductor are called soft superconductor, whereas the type 2 superconductor are called hard superconductors. For example, lead, tin and mercury are the soft superconductors, whereas and NBSN, NBTI is second type of examples in the type 2 superconductor. Next is London equation. This equation was explained by H. London and E. London. Sometimes it is called London equations. For a superconducting state, we know that the magnetic field inside it is zero. What London found that it penetrates inside the superconductor. So it doesn't exclude the superconductor, but it penetrates through the superconductor. So he was explained mathematically. Equation of motion for the superconductor electron under electric field is given by m dus upon dt, that is equal to the minus ee. Here us is the velocity of the superconductor electron, E is the electric field, capital E is the electric field, and small e is the charge, and m is the mass of the electron. Now here we find the current, then we find the current density djs upon dt. Here js is the superconductor current density. We took up the previous equations, then we take the curl of the dj upon dt, and after curl of this so we use the Faraday's law of electromagnetic inductions. Here del cross E is equal to minus dv upon dt. Then solving it and integrating the above equation with respect to time, we found that del cross j is equal to E square ns upon m into b. This is known as the second London equations. Earlier which we have derived dj upon dt, that is called the first London equations. Now it is called the second London equation. Explanation of Meissner effect and penetration depth. Here there are the two different phenomena are there, Meissner effect as well as the penetration depth. Meissner effect says that the magnetic flux lines cannot pass through the superconductor, whereas the London equation says that it can penetrate. So we have to explain here both the effect. Now here mathematically we do the differential form of the Ampere circular law, then taking the curl on both sides. Here we use the rule A minus B, A cross B cross C. Then using the Gauss's law of electromagnetism, we try to find the London penetration depth, and which has a unit of length. After finding these equations, we found that the magnetic field B is x is equal to Vx into E raised to the power minus x upon lambda, where lambda is we already told you that the penetration depth, and Vx0 is the field at the surface, and x is the depth inside the conductor. Suppose x is equal to the lambda, then this equation becomes Vx is equal to the 1 over E times of Vx0. Thus the London penetration depth is the distance inside the surface of the superconductor at which the magnetic field reduces to 1 over E times its value at the surface. This is all about the today's superconductivity. Thank you.